Okay, hello everyone. We are going to do vector semantics today, which are often called word embeddings. Um, so this is explicitly looking at how modern NLP processes actually try to represent words. Okay. Now, many people think this is going to be some sort of neural network based form, and we are going to talk about that, about half of the lectures about the neural network stuff. But actually, we're going to talk about why word embeddings work and what we're trying to do with word embeddings, and actually show that you can come up with word embeddings from an analytic point of view and not just a I'll train from data point of view. Well, actually, all of this is training from data, but there's actually principles in the training of the data, and it actually shows why the neural word embeddings actually work and can be better, but it shows why and what they're actually trying to capture and allow us to be able to evaluate how well they're actually working. Okay. Um, the fundamental problem that we're trying to address here is that words are not in complete isolation. So many words have similar meaning and many words have definitely non-similar meaning. And the way we naively think about words is some token in a list of words in the lexicon is that if they're equal, and if they're not equal, they're equally unequal. And that's actually not right. So in other words, if you think about the word like fast and rapid, they're related to each other. And we would like them in some sense to be more related to each other than just saying if they're equal, fast to fast, and if it's not fast, then it's not equal. Well, rapid should be sort of equal, okay? Same way, tall and height. So imagine that you were building a question answering system and somebody asked the question, how tall is Mount Everest? Um, and your Wikipedia entry says the official height of Mount Everest is 29,029 feet. Now, knowing that tall and height are in some sense similar meaning would allow you to answer that question. But if you don't know that and your machine has no way of actually looking at that and seeing that they're similar, it's going to go, well, I know the height, but I don't know the tallness, so I can't answer that question. So it would be good if we could get a representation where tall and height are way more similar than tall and chair, okay, or some other random word. Why would we want to do this? Well, we want to do this lots of things, you know, question answering. We'd like to do this when we're doing summarization. Here's an example of plagiarism detection where you actually get similarity, and plagiarism detection is almost the same as paraphrasing generation, and being able to get similar things but different. So we'd like to know that, you know, the forms are primarily and usually are got similar meaning. They're used in similar circumstances. They're used to mean the same thing. Used in similar circumstances. Think about that, okay? And that might actually be the way that we could work out that things are actually similar, because if they appear in similar contexts. And historically, people have looked at the use of words in linguistics, in language over time, and tried to assess whether word meaning has changed over time. And actually, you know, in spite of what you might think, language changes. There's always language change over time. How people used language even 30 years ago was quite different to how people use language now. And how people used language 500 years ago was significantly different. On the left-hand side here, we've got three words, dog, deer, and hound, okay? And linguists have looked at the use of these words over time, okay? And actually looked at how many different types of animals they actually cover. So historically, if you go really far back into 1250, that was a long time ago, I only had a short beard then, the word dog, up until modern times, dog was actually a much more restrictive term than what we use it for nowadays. The word deer, okay, was actually a much more general term. The word deer meant any larger animal found in the forest. And so it could include what we now call deer. It also could include, goats, sheep, boars, dogs, and wolves as well. So the word deer was really a sort of large animal that's wild in the forest. And if you speak German, you're probably already aware of that, because the word for zoo, zoological gardens, in German is Tiergarten. And Tier is actually a cognate of the word deer in English, and it really just means animal. Um, Likewise, the word hound, especially a long time ago, really meant lots of the things that we now use to mean dog. And hound is now being a much more restrictive word over time. Let's look at the word gay over the last 100 and something years. The word gay, as most of you know, nowadays means and gets used to mean homosexual. But as also, I think most of you know, the word gay 100 years ago didn't mean homosexual. It meant happy, enjoyable. And it was used in that term, even in the 1920s, to mean, and we can know that by looking at the other words that get used around the word gay, by looking at newspapers and letters and books from that time. And we can see which other words appear in similar context when we go back and look at newspapers from those time, and we can follow it in, maybe not every week, but we could follow it over decades from that time to see how the word gay has actually changed over time so that it gets its modern meaning of homosexual, possibly male homosexual, but sometimes just any homosexual. But its meaning has changed, and that's standard in language, and that happens all the time. And that's something that is interesting to linguists, and it's interesting to us as well, because if you read a book from 120 years ago, you could misunderstand what's actually going on in the way the words are actually being used. Notice that I said people are looking at how these words are used in context, okay? So how do you find out whether a word has a similar meaning or not? Well, traditionally there's a book, a physical book, but they're online nowadays, called the thesaurus. That's not a type of dinosaur. A thesaurus is a book that shows you similar words to a particular word. So you look up a word and it'll give you a list of words that have got similar meaning. Thesaurus doesn't exist in every language, and thesaurus are usually relatively old. At least, you know, they're at least 20, 30 years old, and therefore they miss out on modern meanings. And they don't always capture everything that you would like. They're pretty good for nouns, but they're not very good for verbs and adjectives. And these actually change. And so thesaurus are okay, but they don't exist for us in every language. They can often be out of date. The method that they use to create these things is often some people deciding that these things are similar and trying to come up with other words, rather than actually doing it from the data, which actually would be better if we could try to do it from the data. The fundamental idea that we're trying to appeal to is this, what's called distribution models of meaning. So what we're actually interested in is how do we computationally define the meaning of a word? Now, that's incredibly hard, and probably in a deep philosophical sense, we cannot do that. But is there something else that we can do to actually represent the meaning of words so that we can use them for the NLP tasks that we'd like to do? Question answering, summarization, detecting plagiarism, etc. Zelig Harris, a linguist from the 1950s, noticed that the word oculist and eye doctor occur in almost the same environment. So if you look at the occurrence of the word oculist and the occurrence of the word eye doctor, I personally find the word oculist somewhat old. In the United Kingdom, we would use the word optician, but that doesn't get used in the United States. But even that word optician gets used in the same environment as eye doctor and oculist. And because they get used in the same environment, okay, we can consider them to be synonyms, okay? Now, we have to be a little careful about this. They don't mean exactly the same thing. If you look at a bunch of color names like blue, red, green, you'll find they often get used in the same context as well. And they don't mean the same thing, but they're talking about the same property of the thing that they're talking about. They're talking about the color of it, okay? Firth, who's, you're going to ask me what his first name was. You're not. John, Johann, I think it was. He's Dutch. Not Dutch, sorry, Danish. 1957 said, you shall know a word by the company it keeps. And that's an important thing to remember because, much as these are just quotes from some linguist from over 50 years ago, actually what they're saying is very relevant to the computational techniques that we're going to talk about today. So we are going to consider a word's meaning built upon looking at the context that that word actually appears in, and then trying to measure whether these similar contexts are similar or dissimilar. Okay. So I'm going to give you a little story here, okay? This example, suppose I asked you what the word Tesquino means, and I'm going to give you a little passage. A bottle of Tesquino is on the table. Everybody loves Tesquino. Tesquino makes you drunk. We make Tesquino from corn. And then the question is going to be, so what's Tesquino? I'm sort of assuming you've never heard of that word before. And in fact, I've never heard of that word before, except on this slide. I've never seen it anywhere else, okay? But I, looking at that as an English speaker, and much more importantly, with the bias that I have as a Scottish English speaker, means that if I don't know a word, it's some type of alcoholic drink. Just from, even looking at the context, at least that's what I hope. But actually, there's lots of evidence here that this is some sort of alcoholic drink. So it gets you drunk, it's in a bottle, and people like it. It's made from corn. That's the sort of thing that you might make alcoholic drinks from. And that's exactly what it is. It's a type of beer. And you can work that out because you could replace that word with a bunch of other things. You can think of the word beer. You could put the word whiskey there as well. You could put other forms of alcoholic beverages there, and everything would be fine as long as you pretended it was made from corn. And so you can work out the meaning of a word given the context that it's actually appearing in, okay, without it actually saying Tesquino is an alcoholic drink, okay? And that's an important thing that you as a human do when you're reading the language, and that's something that we would like to get machines to be able to do that. So what we're actually going to say is two words are similar if they appear in similar word contexts, okay? Let's go slide there. 4 kinds of vectors. So we have already talked about some form of representation of words in what we do is a word vector. So we decide on our vocabulary. We add one for not explicit in the vocabulary, the out of vocabulary word. We maybe have a start and end symbol as well, but we maybe got 10,000 or 100,000 vector with zeros and ones in it, and we could represent our information by that in some sort of sparse vector representations. Most of these things are going to be zeros and some of them are going to be ones. And we could say a word's representation is based on the words in the context. And so we could take that 10,000 wide vector and put zeros and ones for each of the words depending on some corpus of data, how often the word, what words appear around the word Tesquino, or whatever word we're actually going to look at. But that's a very wide thing. It's got an awful lot of zeros in it. Yeah, there's good representations that we can actually do there, but the alternative is try to do some sort of dense vector representation. So we could take all of these and actually try to do some computational way to reduce them into a smaller form. We could do some sort of computational way like singular value decomposition, which is a form of latent semantic analysis, to actually try to project those into a smaller form. We could use some sort of neural network to try to take that wide form and predict a smaller form from which we could predict that wide form, that sparse one, again, as accurately as we can. And these are things like skipgrams and continuous bag of words. Or we could do something like brown cluster. Remember we talked about brown cluster when we were talking about part of speech tagging a couple of weeks ago. And we could use Brown clustering to actually try to get a more representation that's denser than the information that we're actually doing if we just say, let's look at all the words in the context and have zeros and ones for everything. Again, the intuition is looking at the context and trying to get that representation. This representation is often called embeddings, and people will talk about them as word vectors or embeddings. Often embeddings are usually dense ones rather than the sparse ones, but really we can talk about these things in the same form. But much more importantly, instead of just getting the word number or the word in the list, so our representation of tall and height are just two distinct integer numbers in a big list, we're actually trying to get a representation that would allow us to do distance metrics. That's what we want it to be able to do, okay? So this is what's called vector semantics. And the first thing we're going to do, we're going to look at co-occurrence vectors. So we're really going to look at the context that things are actually in and try to sum them up. So what we're really trying to say is, given a word, we could look in the document and see which words appear in the context, or we could do it word to word, and we could do it in some way. So imagine we take plays of Shakespeare, okay, and we take particular words, and we're going to see what their occurrence is, their number of occurrence in plays in Shakespeare. So we take the word battle, and then we've got 4 plays, As You Like It, Twelfth Night, Julius Caesar, and Henry V. Don't worry if you've not read these plays, or you have read these plays at school and you absolutely can't remember the content whatsoever. That's not important what we're doing. Very quickly, you'll see what we're trying to do. So battle appears once in As You Like It, once in Twelfth Night, 8th in Julius Caesar, and 15 times in Henry V. So it appears more often in the Julius Caesar and Henry V. Soldier appears a couple of times in As You Like It and Twelfth Night, and in Julius Caesar appears 12 and 36 times. Let's take the word fool. The word fool appears many more times in As You Like It and Twelfth Night than what it appears in Julius Caesar and Henry V. And the word clown, well, the word clown doesn't get used very often, apart from it's really quite a favorite in Twelfth Night because there's a character, there's a clown called Bottom, actually, in Twelfth Night. Even if you don't know what these plays are about, you can probably already see some pattern that the words like battle and soldier are more common in Julius Caesar and Henry V than they are in the other two, while fool and clown are more common in the other one. That's something that's actually useful. We're going to make use of that. So that count vector, okay, is actually telling us the number of words. That's not going to be ideal because maybe we want to get some sort of normalized probability there, but it's a good start. We can actually say if 2 documents are similar, their distributional occurrences of the words are going to be quite similar. So in other words, Julius Caesar and Henry V are more similar plays to each other than they are to the other 2, okay, which is actually true. Okay, Julius Caesar and Henry VIII is all about kings and Caesars, emperors, beating each other up and trying to take over the throne, because that's what kings do. Well, actually, let's be fair, that's what stories about kings do. Kings often don't end up doing that. They always end up in exile. Likewise, we could also look at each word and try to find out whether they're similar based on the distribution, okay, across these other documents. So from that, we could say that the word fool and clown are more similar to each other than to soldier or battle because they've got a similar distribution in a particular document. Now, that might not be true that they're similar words. It might just be that they're closer and more likely to appear in such documents, okay? But it tells you something about the relatedness of these words, okay? And definitely it seems like fool and clown are more similar to each other than fool is to soldier, while soldier and battle are more similar to each other or related to each other, okay? Doing it in a whole document, a whole play isn't always the right thing to do. Maybe we could actually try to restrict it. Instead of doing it per document, we could do it per paragraph, or we could even limit to a number of words at either side. And that's often what we do. we have advantages that if we did it on the whole document, we'd be able to get better statistics quicker. They might not be exact, but we would get numbers to differentiate quicker. If we're just going to do it with 2 words at either side, we'll need a lot of examples before we're going to get reliable statistics. So this sort of work can only really work well when we have an awful lot of data. And so we have to be aware of that. So we're not just talking about, we're going to do it on 12 articles from Wikipedia. We've got to do it on all the articles of Wikipedia. And maybe we want to do it on more than that so that we get better statistics. Okay. So for example, what we can do is we can look at the context with 7 words before, 7 words after, and we can start collecting them for apricot, pineapple, digital information. So we can look at the word apricot that appears in the first line there, and we notice with our other words along the top that could appear in the context. Now, of course, that's really going to be incredibly long. That's going to be our 10,000 word wide vector. So we've just highlighted a few of them here, and the rest of them are off the side of the slide. And so aardvark, computer, data, pinch, result, sugar are just small examples, but for apricot, pinch and sugar appear. For pineapple, pinch and sugar appear. For digital, result appears and data appears in its context, etc. Okay. And so we have these 2 words that actually are in common between apricot and pineapple, and that might be telling us that these 2 words are similar. Okay. Likewise, digital and information have got lots of zeros, but we also got lots of positive numbers in areas where there's some similarity. Okay. Of course, that matrix is actually really wide. It's got however many words we are, 50,000 words. Most of the values in it are 0. There are very good representations that we can have of sparse arrays. Most programming languages provide you with a way of actually doing it, libraries to do that, but it would give you the information and we could collect that information from documents, okay? One thing to consider is that there's what's called first order co-occurrence, okay? And that is that the word wrote is in some sense similar or related to the word book or poem, because book or poem actually will appear in the context of wrote, while there's another way, which is a second order, and that is wrote's arguments, the things that appear in its context, will be the same types of things that appear in the context of say and remark. So one is we're talking about the relation between a word and the words that would appear in its context. And the other one is we're looking at context and seeing what words can be similar between them. It's just a different way of looking at the same information. We have that information, okay? So we're now going to introduce this notion of positive point-wise mutual information, PPMI, okay? The raw word frequency that we were talking about putting these is not actually very good. It's very skewed. When we start looking at words like the and off, which are incredibly common, we're going to get really, really large numbers there. And they are not the interesting ones. The ones that are actually interesting are like the content words, which are differentiable and they make a difference in the context. While almost everything will have the and off a lot of the time. Okay, and what we'd really like is a piece of a measure of information to actually tell us whether these words that appear in the context are particularly informative. So what do we mean? So we're going to actually define this positive point-wise mutual information as a thing that cares about how informative is this word given the context that it's actually in. It's quite simple when you actually think about it. So it really is that you have a probability of 2 words. You have the probability of word X and the probability of Y. And what you want to know is how independent are these words. So we can have the probability of X and the probability of Y, or we can look at the probability of XY. Okay, so what's the probability that they appear together versus the probability that they appear independently? Now, once you work out that's what you want to do, we're really trying to look at this ratio between the probability of the both words appearing as opposed to the probability of each. So we could multiply together the probability of each, and we're trying to get that ratio, and we flatten it with the log, and that is what we call the pointwise mutual information. So it's not the positive pointwise mutual information, it's just the probability, it's just the pointwise mutual information, okay? And that actually tells you about how likely these words are to appear together, as opposed to how likely they appear independently. And that becomes quite a good measure of how important they are, okay? How much information that they actually have. Now, PMI actually is going to range between -infinity and infinity, okay? But the negative values are a little weird, okay? And what we'd be saying is that their co-occurrence is less than we expected them to be by chance. So it's almost as if, it's sort of hard to describe. It means that these words rarely appear together, but they independently have got some other form. Maybe they are conflicting, so they might actually be opposites of each other. So, you know, left and right might not appear together. Well, when they actually appear together is only when people are actually contrasting things, maybe. But the things that have a value below zero are usually a little weird. Because of that, we'd like to be able to just ignore them. And actually, let me give you a stronger reason of why we want to ignore them. We actually care in this measure about how close things are when they're close. We don't really care about how close things are when they're not close. So for example, I really would like to know how close the word green and turquoise is. But in my processing, I'm happy just to know that chair and Nebuchadnezzar, my favorite word, Nebuchadnezzar and chair, are just different. And I don't actually care whether chair and Nebuchadnezzar are further apart or closer than computer and fork. Okay, I just don't care. They're just different. And so I just want a threshold for that. And I don't care about super optimizing for the distances between things that I just know are different. So what we typically do with pointwise mutual information is we actually put a guard on it, and we actually say we don't care about anything below zero. If it's zero, if it's below zero, let's just call it zero, okay? And this is why we talk about positive pointwise mutual information, okay? And it makes some of the math a wee bit easier. It also means that we can actually care about some of the other tricks that we're going to talk about, where we're really going to try to optimize about the interesting distance between things rather than just the distance between everything, because that often doesn't really help us in the tasks that we're actually doing. Okay, I have quite a lot of slides in this today, and when I'm giving this lecture, I will typically skip over some of the math, the forms, but it's a good idea for you afterwards to have a look at this. Also, as David Mead tell you all the time, we actually have a book for this course, and it's really, really good, okay? And you should read it, okay? So in addition to watching this video, looking at these slides, it's a good idea to actually read the Jurafsky and Martin book as well about word embedding. A lot of what's actually out of here is out of one of the particular chapters, okay? So we can, instead of, we're going to go back to our pineapple and apricot example, and so instead of just having counts, where we don't, the actual number of instances may actually be biasing things in directions that we don't really want it to be. What we can do is we can actually replace these numbers of occurrences, not just with the number of occurrence, but we can put in pointwise mutual information, positive pointwise mutual information. Okay, this is the math. It's right. As if you'll check it. It should give you points if you actually check it and find out what the answers are. But you can look at this afterwards. Again, see, I told you there's always going to be more story with pointwise mutual information. It's actually still a little biased towards infrequent events. Very rare words may have higher pointwise mutual information than sort of they really should get. because it might be that you have so few examples that their co-occurrence can actually be well estimated, and therefore they're effectively getting a bigger boost than they really get. And you actually might be missing some things of even rarer things that didn't appear in your data. So it might be a good idea to actually see if we can smooth that in some way. And if you remember from the lecture from smoothing, more than 2 weeks ago, we talked about add one smoothing, Laplacian smoothing, okay? That boosts rare words a little and gives slightly higher probabilities. And that actually can help us. So what we can actually do is give rare words slightly higher probabilities than low probabilities. And that actually smooths the pointwise mutual information a little better. So in other words, it has the effect of caring about the low end, the low frequency words better than the high frequency words. And the high frequency words, it's okay if you flatten them a little bit because you have better ways of estimating with them. But the low frequency words, you want to get something that actually tells you a little better. So things like add one smoothing to your, before you calculate pointwise mutual information, actually typically does a little bit better. Okay, so again, a bunch of math. We can do this. It flattens the numbers a little bit. So let's move a little bit now on to similarity, in particular cosine difference. And you'll be, if you've seen this stuff before, you'll know where we're going. If you've not seen this stuff before, you'll think I'm just actually generating random words based on a trigram model, but it's more complex than the trigram model, I promise. So what we'd like to do, and if you think way back to the first example that I had in one of the early slides, I was trying to get, can I get a distance metric between tall and height so I can know that these are similar or rapid and fast? And so I would like to get a representation that allows me to compare it and get a distance metric that allows me to say whether they're similar or not. Now, if I have two vectors, I could multiply them together and actually try to find out whether they're similar or not. Okay, and after you have a definition, the most easy way to do that, I do just multiply them together, and where there's two numbers together, I multiply them. Of course, if there's zero, it's going to be one of them zero, it's going to go down to zero. Okay, and so in other words, if they do have numbers in the same position, we're going to get a positive thing. If they have many occurrences, it's going to be positive, positive, a high positive. If we're going to have 0 on one, okay, and some number on the other, that's going to move down to 0. That's going to be a mismatch, so it's going to pull its weight down. If they're both 0, well, that means they could be 0, but the number is going to be 0, but that's not going to boost their similarity. Okay, so we're mostly looking at the positive examples. If they're similar in the positive examples, we're going to get a higher value. If they've got a 0 on either side or both sides, it's going to lower the similarity. But remember, most of these vectors are going to have many, 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 many zeros in them. So it's okay. So in other words, most of the zeros are going to match. But there can be problems with this. The longer the dimensions of the numbers we have, we're going to have more numbers, and so the magnitude of the distance is going to be different. And so it's sort of going to be hard to compare a distance metric when we've got these two words as opposed to these two words over there, because depending on the number of greater than 0 numbers that we have in these two vectors, we'll get a bigger distance, okay, compared to the other one. So it's going to be very hard to know that when I'm comparing these two words, and the difference is 357.5, is that a big number or a little number? And that gets hard to do because each distance between two words effectively is got a sort of expected different magnitude. So it's hard to come up with an overall score of what means is similar and what means is not similar, okay? So we can actually use something else. What we could do is we could divide by the number of the length and divide by the number of examples that are in it. So what we could do is we could take the two vectors and we can multiply them together, and we could divide them by the length of the two vectors as well. And that sort of works. And this is the bit that isn't immediately obvious unless you really think about it. And if you don't understand this, don't care about it, just take it as fact. If you do care about it, it's actually obvious when you actually think about it. That expression is actually the cosine of the two vectors. So these vectors are actually in n-dimensional space, and they're pointing in some direction across different dimensions. And the angle between them, okay, can actually be measured with cosine. And therefore, that expression actually gives you the cosine, okay? And we call this cosine similarity, okay? And it's not immediately obvious why this is the case, but it is. And it really is talking about that dimensional aspect of which I have got. So we have the dot product, we have the unit vectors, and what you actually get is a number out of this that's going to be on the cosine curve. So it's going to be between +1 and -1. And actually, we don't really care about the things below 0. The things below 0 are really saying they're not like each other at all. They're really far away. That's very similar to this, the same justification that we treat with the positive pointwise mutual information. And so if we're just looking for positive pointwise mutual information in our forms, actually the range of the distance is going to be between 0 and 1. 1's going to be more similar and 0 is going to be less similar, okay? And then we got a bunch of math about how to do this. So it really is an angle. And so, you know, if we only had 2 dimensions, imagine it's much easier to see angles in 2 dimensions. So we can have these 2-dimensional things that we have in an XY plot, and we really are talking about that position, about how close they are, okay? We could then take all of our data, we could calculate co-occurrence matrices for everything, and so we could calculate what the representation in positive pointwise mutual information is for everything. We could then try to get our cosine difference between everything, and the things that are similar we could cluster together into a single cluster and build a tree that looks like something like this on the right hand side. And so somebody did this in 2006 for some data set, don't know what data set, okay? And what we end up with, if you look closely at these words, which I can hardly see, we discover that wrist and ankle at the very top are very close to each other. Yeah, they're sort of similar type things. Yes, they're different parts of the body, but they're very similar. And then things like shoulder, arm, leg, hand, and other body parts are put into the same class. They don't mean the same, but they're relatively close to each other, okay? And so we can do that over all of our data. And now we have a distance metric, and now we have potential clustering for all of that. Cosine similarity is only one particular way of doing it, and there's lots of other ways depending on what you're trying to emphasize, also depending on the type of data that you actually have. If you've got nice, clean, lots of good data that are really covering the space that ultimately you're wanting to use, cosine similarity is a good measure to do. And in fact, you should probably use cosine similarity first and see how well it does before you start looking at the other ones. But there are other ways of trying to slightly emphasize either higher frequency, less frequency, caring to optimize about very close cases to boost them so that you get much more accurate numbers, and when it gets further away, it gets less accurate. But it depends on what you actually want to do. If you're trying to cluster everything to everything else, cosine is probably better, but sometimes you want to do something that's a little bit more sensitive to the actual distance when you're close. All of this was looking at words in context. It wasn't using syntax in any way whatsoever. But you can actually do something more than just caring about the words in the context. You could actually look at the syntactic structure of the words. So remember, again, some time ago, we talked about dependency parses, and I told you about how to be able to get dependency information out of a parse tree rather than just get constituent information out of a parse tree. So the dependency with these things that had longer arrows for them rather than it was a tree. And what we could do is, instead of using the context to be the 2, 3, 4 words and round about the word that we're actually dealing, we could actually take the words with the arrows round about it. The advantage of that is now we're actually going to get context that cares about maybe the verb and the head noun that we're being related to, rather than just the word distance. We're actually getting, in some sense, the syntactically local things rather than the surface context things, okay? And that's surprisingly easy to do. So we just say, instead of taking the 4 words before and the 4 words previous, we get our dependency parser. And what we do is we take for each word, we basically follow these links and take the 4 closest words that are there, but we always take them in the same order. And many dependency parsers will actually label their arcs. And so you want to make sure that you keep the same arcs when you're looking across different words. So this works, and it can work actually quite well. It does depend on you having a good dependency parser, but for standard English, that's not very hard. And actually for, the top 10 major languages, there's pretty good dependency parsers for all of them. And realistically, it's probably never going to be worse than the just looking at the 4 words before and the 4 words afterwards, because often when the dependency parser sucks, it almost falls back to that and has almost the same information in it, okay? So we just do the same thing, okay? So we can do the same thing with dependency relations. Rather than just looking at words in context, we have these numbers there and we build our PMI, and what we end up with is, instead of just having the words that are in context, we might end up with, in fact, we usually will end up with, what types of arguments does the verb take? And that's a pretty strong indicator of the type of word. So what's the most likely word that we have with drink? And if we were just looking at word occurrence, we might find that it is the one, but it's not a very good one, even though that might be much more common than getting a word like wine, which would be a better exemplar, if you like, of the sort of object that goes with wine. There's another measure that we can use as an alternative to PPMI, and that's TF-IDF. TF-IDF stands for term frequency. So it's the frequency of the word. So it's the probability of the word in all of the document that you have. Sometimes we flatten its distribution by taking the log of it. And then we also have the inverse document frequency, IDF, okay? And what we're doing there is we're basically finding out how often does that word appear in that document compared to other documents, okay? And so what we're really interested in is, does this word appear more often in this type of document compared to other type of documents? So is this a discriminator word? And what we're really looking at is trying to take into account the overall frequency of the word versus how often it gets distributed over all of the documents. Okay, so if we have a bunch of documents that are all talking about Linux commands, okay, and they've got the word shell in them, and then we've got this other bunch of documents and all they're talking about is Harry Potter things, okay, shell probably appears much more in the Linux ones compared to the Harry Potter ones. Yeah, I know you're all immediately going to look up Harry Potter and find the occurrence of the word shell, okay. So let's go back to this idea of sparse versus dense. Really, in everything that we've been talking about so far, we're still expecting them to be sparse, but we're talking about how to get that information into the pointwise mutual information measure or some other measure. That's what we're trying to do. And so we end up with these really long, really wide ones. You have to decide the vocabulary. Actually, you're always going to have to decide the vocabulary, as opposed to the sparse ones that have got most of the elements, the sparse ones, most of the elements are 0, while there's a few of the elements that have actually got non-zero. Can we get them to be much shorter? So we've only got, a few hundred examples, so that most of the things are non-zero, okay? Why do we care about this? Okay, it's a computer, it should be able to deal with that. The computer's really going to complain about the number of numbers it's going to deal with, but that's its job. And the answer is, well, yeah, that's sort of all right, but from a machine learning point of view, it's computationally expensive to deal with 50,000 numbers every time we want to multiply by an array, while getting it down to 1,000 is a lot faster because actually it's squared in there. So often you're doing matrices, and so you're doing 50,000 to 50,000, and that's a really big number, while 1,000 times 1,000 is only 1,000,000, and we know that isn't a big number. Can we do something? Can we project that sparse matrix onto something that's a little bit more dense, that tries to keep it more compact? It also, remember, we're losing a piece of information. So although we get these matrices for a particular word and what its context is, but one of the things we sort of lose from this is the words in context. So supposing we have a word like car and automobile, and I'm going to naively assume that these mean effectively the same thing. If you have a column in your form for car and one for automobile, it sort of doesn't matter for when you're building your matrices whether the context contains car or the context contains automobile. And what we'd really like to do is sort of maybe merge these columns, because that could be a more efficient way to be able to look at it. And so instead of having individual words along all of these columns, maybe we could have clusters of things somehow efficiently to do that. That sounds like a great idea, but how can we do that? And how can we measure that we actually are getting what we want to get out of that? So we're going to talk about 3 different ways to be able to do this. Okay, the first one is mathematical technique called singular value decomposition, SVD. It's actually a special case of latent semantic analysis, LSA. The second class of things is word embeddings in the neural language model point of view. So we're actually going to try and estimate some representation that's smaller with neural nets and be able to force it to contain the information. It's going to do some sort of nonlinear processing through its multiple layer in order to be able to do it. And we'll talk in some details about this. Sometimes they're just lookup tables for particular words, and sometimes you have to give it full sentences where it cares about the contextualized form of the words. And the last one is going to be Brown clustering that I'm going to talk about. So let's talk about SVD. So basically we've got this n-dimensional thing with very large n. We'd like to be able to project it into something that's fewer dimensions. We can do this by rotating axes, because remember, it's really this position in n-dimensional space. We can try to reduce that. There's a number of standard algorithms that allow us to be able to do that, and that includes principal component analysis, factor analysis, and SVD. They're all in the same space of taking larger representations and trying to project them. And what they do is they try to find the correlated coefficients in there and actually merge them. Remember, I mentioned about car and automobile, okay, is actually being somewhat similar, and it would effectively allow to look at the distribution of car and automobile and notice that they've almost got the same values everywhere, and maybe exactly the same values, but almost the same values, and therefore the amount of information that we would lose by collapsing those may actually allow us to contain the same amount of ultimate information. And we do this just by actually looking at the numbers. We don't really care what they stand for. And these techniques are, agnostic to the meaning of the values, though sometimes you have to care about it. The fact that we're dealing with counts rather than genuine continuous values can be an issue. And even if we've got probabilities, but remember, these are estimated from counts, so they're not as accurate as we would like them to be, and so smoothing, etc. And they're noisy. Both the data we collected is noisy, and the fact that we're going to try to reduce them will lose some information, but it's trying to lose the least amount of actual information. So dimensionality reduction, basically what we're trying to do is we look at one particular dimension. We can calculate the that linear form and the relationship between it. We can effectively remove that and flatten it and just contain the information that's got the bit left over, and then we can look at the bit left over and equally do that. I'm not going to go into detail because I've only got 20 minutes left. But SVD is a very standard algorithm. it's a special case of LSA. It's been around for an awful long time. Often we reduce everything to 300, and I have had the question before, why 300? And I have no idea. And I've asked other people and they go, I had no idea either. And the best answer we can come up with, the first people who started doing this had the size of their machines such that the problem they were working on, 300 was good for them because it allowed them to fit their data in afterwards. So there's not a good answer for that, okay? But going from 50,000, a vector of 50,000 wide down to 300 is a good idea. The fact that you end up with a dense representation out of that seems to be a good result, and also when you use it for tasks is quite good. But you know, you could go for 100 or you could go for 1,000, and unless you actually test it or for your particular task, it's not clear whether 300 is actually the best or not. Okay. Can we apply SVD to pointwise mutual information? Of course we can. So we end up with a reduction of that. Let's look at the second class of vector length reduction. And this is looking at neural nets. Okay. Particularly, we're going to look at skipgrams and continuous a bag of words. Okay. And then I'll say a little bit about BERT, but we're actually going to talk about them in a later lecture again. Skipgram is really appealing to the same idea, and the idea which had been around not for words, but had been around in both vision feature reduction and in speech feature reduction, where a large number of features are often continuous, are being reduced into a smaller dimension that may capture the information that we actually want. And usually the way that that was done was that they took a large amount of features, they tried to build a neural net that would predict a smaller number of features, and from that smaller number of features, they would try to predict the original, okay? So in other words, they were forcing whatever the reduced form was not losing information that could still be projected out again onto the original, and you would try to minimize the unpacking. And skipgrams and continuous bag of words, although they're slightly optimizing different something else, are very similar, okay? So we want to train a neural network to predict the neighboring words, or we want to train the neural network to predict this word given the neighboring word. So that's really the distinction between them. Again, we're fundamentally basing this information work, the information we're giving to the machine learning is, let's give the context for these words and assume that the context sort of defines what the word is. So the representation is being trained by looking at some contextualized information about the word. So we're looking at a word and we're giving it 4 words either side, some number of words either side, okay? If we get this to work, it could be much faster to do than SVD. SVD is computationally very expensive. And actually, much more importantly, if we can do this, we could pre-calculate it. We could pre-train it, which is now the standard term, and we end up with a model which exists online and has been compiled with some large amounts of GPUs that Google has, and you just use it in your program. So you go, I need the vector for Nebuchadnezzar, and it gives you the vector for Nebuchadnezzar. I need the vector for soldier, and so you get the vector for soldier. And so that is certainly an attraction, okay, that allows you to be able to pre-train and get some lexicon of words. And sometimes you'll say, I want Nebuchadnezzar's, the plural of Nebuchadnezzar, and it'll go, I have no idea what you're talking about, but here's my unknown word representation. So you can get a form of that, okay? Skipgrams can also be trained on your own data. You don't actually have to go and use the Word2Vec pre-trained, but you can train from your own. And depending on the amount of data that you actually have and the difference your data is to the data that the standard Word2Vec data was trained on, and you might still be in the same language, but you might be in some different domain. So The Word2Vec stuff was mostly trained on books and Wikipedia and news. But if you're doing Twitter, it's not very appropriate because that language in Twitter is not really the same as what you get in the Wall Street Journal. Okay, so you have some choice, but then do you have enough Twitter data to be able to build something that's better than Word2Vec, which is not ideal, and you probably have to do an experiment to be able to work out for that. Okay, so I'm going to go to the little picture here. Right, so first what we're going to do is our input. Okay, what we're going to do is we're going to again have this big vector, and the input that we're going to give to the system is a big long vector that's our 10,000 wide, and what we're going to do is put a 1 for the word that we're actually dealing with. So if Nebuchadnezzar is word 3,457, all the rest of them are 0, but position 300,457, or 6 if you're 0 start, will have a 1 in it, everything else will be 0. Okay, and that's how we represent words. It's often called one hot. And what we actually want to do is we want to build a neural net like this, where what we're doing is we've got this really wide one hot layer that comes in, some number of fancy layers here, just fancy layer, I mean, nothing special here. And then we'll have a smaller internal form. Let's say our magic 300, doesn't have to be 300, but let's call it 300, something that's smaller. And from this, we're trying to predict, again, 2 outputs. One of them is the one hot of the word before Nebuchadnezzar, and one of them is the word after Nebuchadnezzar. Okay, and so our training set becomes the representation for Nebuchadnezzar, and the representation for the word before Nebuchadnezzar in their data, and the word after Nebuchadnezzar in the data. And what we're trying to do is we're trying to predict the previous and the next through this bottleneck of limited forms. And once we've trained it all, we're going to say that this is a representation that we know has the information of the word, or we assume it has enough information about the word that it can reasonably reliably predict the previous and the next one. Okay. And then what we're going to do for encoding is we're just going to say, we're going to put this in, we're going to calculate this, and we don't care about this, and we're just going to say, this is our representation in the middle for each of the words. And so Word2Vec, it's a big lexicon of words, but we don't have to represent them like this. We can just represent it as a single word. We don't have to get it in the one hot form, and we just look it up and we get our 300 random floating point numbers back. They're not random, but you won't see any pattern in them. Okay. The continuous bag of words. Yes. Are these things different? And the answer is, yeah, that's actually quite interesting. So are they capturing the same sort of information as point-wise mutual information? And there was a piece of work that actually tried to see if they were correlated, Levy and Goldberg, in 2014, to see whether Word2Vec representations had any correlation with PMI. And it appears that they do, although it appears that they're actually slightly better than PMI because they deal with these low frequency cases quite a bit better. So there's smoothing that's magically happening. I believe that's a good technical word for neural forms. So it looks like they are sort of trying to do the same thing. So point-wise mutual information was in the right direction. But it looks like that skipgrams can be competitive with them if they have the right type of data. Okay, this is always the case in the machine learning if you have the right type of data, and you should always think about when you're ever using this, do I have the same type of data as what that person trained their pre-trained model on, or am I far enough away that I'm not going to get the benefit and I have to do it myself? Continuous bag of words is very similar to skipgram, but okay, instead of trying to predict the context, what we do is, given the context, can we predict the word? So we just inverted it around the other way, and we end up with representations that represent the context of everything rather than what the words are. If we then take these 300 wide vectors and try to find the most similar words or phrases to those, we find that it actually does things quite well. Again, using, say, cosine similarity, it's a perfectly reasonable thing to do. Although you maybe thought cosine similarity was good for the sparse cases, actually it's pretty good for the dense forms as well. And so what we find is that Redmond, Redmond, Washington, Redmond, Wash, Microsoft, okay, Microsoft is only the name of a company in Redmond, Washington, but it gets used to mean Washington, like Washington, D.C. gets used to mean the US government, or the White House gets used to mean US government. Havel, Václav Havel, President Václav Havel, Velvet Revolution. Václav Havel was the president of Czechoslovakia, actually after the breakdown of the Soviet states and Eastern Europe. It was called the Velvet Revolution. So these are similar to each other. Ninjutsu is related to ninja martial arts. Swordsmanship, graffiti is related to spray paints. Graffiti is spelt differently, and taggers, etc. So it does get things that are actually similar. Embeddings also do something else. Now, this looks ridiculously exciting, and this is the sort of thing that conspiracy theories get built upon. And please don't think it's quite as good as what it appears in these examples. There have been later work to try to show that this isn't fully general, and the sorts of things we get is not unexpected because of word distributions and the relationships to word distributions. So it was noticed that if you get the vector for the word king and you subtract, as in, you know, minus, take all the numbers away, the representation for man, and then you add the representation for woman, it is close to the representation for queen. So that implies that within the actual representation, this dense representation of random floating point numbers, it has something about being male, okay? And the representation of woman, okay, has something about being female, such that when you move the king to queen one, what you do is you get a gender change, but you still get the head of state out of it. And this happens for a number of things. So you relationship between Paris and France, subtract France, add Italy, you get Rome being in there. And people have noticed this, that, oh my God, it actually understands dimensions of the semantics of the word. Although there's been later work saying, actually, no, it's not really quite as strong as that. It's just that there are certain classes of things. So if you look at king and look at a wider class in that particular space and n-dimensional space, what you find is eventually, if you move out far enough, you get male, okay? And so it's not really the case that what you're doing is you're moving from one to the other. What you're really doing is you're moving within an already predefined, it's probably not simply hierarchical space, and therefore it's not quite as general as it is. But this is quite interesting. It does tell us that there is information that are in these vectors that is quite useful for doing interesting NLP tasks. And that's certainly the case. These representations suddenly allow us to do much more interesting things that were actually quite hard, or we needed an infinite amount of data rather than just an infinite amount of data. Can I train my vectors in all of Wikipedia? And the answer is yes, but only if you manage to trick us to get enough new AWS credits, because it's actually quite computationally expensive. But you do not need to do that. As we all know that Google has more computing power than anybody else, maybe Facebook has more, they've already pre-calculated it. So actually Word2Vec is a Python form. I mean, it's not a Python form, but it has a Python interface that will allow you to be able to use pre-calculated vectors. And that's a good thing to do, okay? That if you want to actually get a representation of words, you pre-calculate one. Instead of Word2Vec, there's another one called Glove, which is actually, most people don't look at this closely, but Glove is an analytical form using pointwise mutual information with some fancier tricks than what we talked about here. And sometimes Glove is better. But again, it really depends on the particular data that you're doing and you're wanting to use it for. But there's always more. Word2Vec and Glove give you a representation for each word. So you ask a word, you give it the word apple, you get a representation back. So it doesn't care that apple has multiple meanings. It can be a fruit, it can be a computer company, or it can be a computer. okay? So it can be any of those. So it doesn't care, and it sort of puts all that information together. But BERT, and actually its predecessor, Elmo, are contextualized word embeddings. So what they do is you have to give it a whole sentence. So now you've got apple in the middle, which might be followed by carp, or it might be followed by computer, or it might be followed by delicious, okay? And I don't think the computer's delicious, but I've never eaten it. So depending on the context, you're going to get different vectors for each of the words. And this has been shown to be much, much, much better. Much, 3 better, okay? It's maybe not 4 better, but it's 3 better. But BERT as a model is much bigger, and you've got to get the full sentence. It's computationally more expensive. Actually, Google again has an interface to be able to do that. Now, when BERT happened in November 2019, almost overnight, everybody changed their word vector representation to use BERT because it's always better with BERT, okay? Now, since BERT came out, and if you read the original BERT paper, it was quickly pointed out that the Google group who made it, Devlin et al., said, we made some choices and we didn't really investigate the whole space, but we made some choices on the best way to be able to do it. So they really are caring about the context. They're actually using transformers as the representation. So they've actually got words within the context, any word within the context of the whole sentence can actually feed into the importance of the representation for the vector. So they're not limiting just to 3 or 4 words, they're looking at the whole sentence. They're also looking the words afterwards and not before, which makes it not really a language model, so you can't use it for some things you'd like to use it for. And other people, since BERT came out, has looked for things which are alternatives to how you set up contextualized word embeddings with transformers as the technique. And they've got better results, okay? And actually for a while, I'd say last year, almost every week somebody would come up with something that was better than BERT. I mean, it was marginally better than BERT, and BERT was much better than things that were happened before, but it was better, okay? Sometimes it was training on an awful lot more data. Sometimes it was training on noisier data, so it actually meant that it dealt with the noisier cases better. Sometimes it was training on different data, social media things, rather than news and Wikipedia. Many of these new things that came out ended up with the word BERT inside them. So there's things like Roberta came out, and there's actually one that's been designed as a language model that's called BART rather than BERT. So changing from Sesame Street to The Simpsons. I don't think that's an important part of it. But BART does other things as well. The one came out of CMU last year, XLNet, from one of our PhD students, which was also substantially better. And it basically looked at the contexts, and what it did was actually flip the contexts around in order to be able to get better training looking at the context and contrastive training looking at the context. And that made a difference as well. Not all of them are readily available online with large enough models that you would actually want to use. And so often people fall back onto BERT or multilingual BERT or Roberta or Albert, or I can't remember them all. But BERT itself is often quite reasonable. Again, all of these, Word2Vec, Glove, BERT, any of these, it depends on whether your data is like their data or not, whether it's really going to work. If you're dealing with Twitter, if you're dealing with a dialogue system that's talking about very different distributional forms of words than what was in Wikipedia, it's probably not going to work, and maybe better to train your own embeddings. But then it depends on the amount of data that you have. Brown clustering, almost finished. We talked about brown clustering before as an alternative to part of speech tagging, with the idea that what you can do is you can try to put words into classes. Now, part of speech tagging very much is trying to get a syntactic similarity. So we want to have all the nouns together, all the verbs together, all of the prepositions together, all the pronouns together. But brown clustering says, I'll take all your words and I'll tell you the distance between them and put them into a tree that would allow us to be able to represent that distance metric in all the words in your corpus, all the words in your corpus. So you have to process all the words in your corpus. Brown clustering is pretty expensive to actually run. What you can actually do, I'm going to skip that, what you can actually do is once you've made that tree, you could convert that tree into word embeddings for each of the words in it. So you could use it for clustering things. So you look at some point in the tree and take all the words below it and say they're in the same cluster. But what you could also do is start at the top, because the Brown cluster tree is a binary branching form. You can name the left one 0 and the other one 1. And as you move down the tree, when you get to the end, you'll have some route that you took left or right, and you label them as 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, and you get something at the end. And that route can be an embedding. Okay, that route gives you a bunch of numbers. Okay, you can then make it into a bunch of a big integer or a bunch of bytes, doesn't really matter, okay, or just zeros and ones, okay, but you can actually collapse it into bytes, because most of the techniques that we have can deal with that in a reasonable way. And so you'll get this big long thing, and basically as you move along it, you're going to get more and more similarities. So the least significant digits, if you like, in your embedding, okay, are going to tell you that things are closer together. Now, I just like to point out that the embeddings that we get from Word2Vec are best described as randomly ordered floating point numbers. They have no order to them whatsoever. Actually, it's not true that they have no order, but they have no intended order. So it's really hard to be able to know if things at the right-hand side of your vector are less important than things on the left-hand side. So you just don't do that. And things could be all over the place. And in fact, in most of these algorithms, they have a random start. And so every time you train it, you're going to get different results. Okay, so if you use Word2Vec to be able to get things, and somebody retrains Word2Vec, you can't use that Word2Vec to be able to do comparisons. It's not going to be in the right space. Brown clustering, however, has got this left to rightness, and sometimes that's a useful thing to have. Brown examples over some set is lumping together, in this case, days of the week, months, etc. So it sort of does reasonable things. Let's skip that. How do we find out the similarity? We talked about using cosine, but this is something about a downstream task. Can we use that to be able to help our tasks? And so we can use it for question answering, spell checking, can we find the alternative for spelling? Can we do it for grading? And people have used this also from a task that humans do. If you've ever done the TOEFL things, because you're a non-native, one of the types of tests that they have is, say, levied is closest in meaning to, and give you a bunch of other words. And humans do this, okay? And you've got to be relatively good at the language to understand how you have to know these words and how they get used. Using that data that gets used for TOEFL, we could then try to externally measure how good word embeddings actually are. Word embeddings are pretty good, but they can get confused. They're not, I mean, they don't really understand the language, and it's important to remember that, okay? So what we've talked about is distributional vector models of meaning. So we're talking about a bunch of floating point numbers that is trying to represent the meaning of a word. Given a word, we get these bunch of things. We want the thing that we get out of it to have properties like distance metric in the domain actually is something to do with meaning, but much more importantly, useful for our downstream tasks. We talked about sparse ways of doing this, either just looking at co-occurrence, but also trying to get a better representation of that, and talking about positive point-wise mutual information, okay? Then we talked about 3 ways of doing it in a dense form, and this is like taking something like our word co-occurrence or our PPMI representations and trying to project it into a lower dimension so that we can also do distance metrics there. And therefore it's more efficient to actually use, and may even capture dimensions which we cannot get simply from the sparse forms. We talked about learning these from neural nets. So this is skipgrams and being able to run them for you, or to use offline ones that have been pre-trained in order to be able to get good representations in order to be able to do it. I should say BERT is 768, or big BERT. There's a big BERT, and it's, I think, 1024 wide. So they're still quite big. And I talked about brown clusters, which is, again, analytical way of doing it. And realistically, it gives you much smaller numbers. It's much more targeted to the particular data set that you have, but you have to make sure that your training and test is in the right domain in order to make that useful. Okay. That is it for today. And I now see there is a question here, which I have to move to be able to read. Sorry, I missed this. Back in the questions about PPMI, why is it good to give the rare context words higher probability? Usually the rare context words, you don't have a good estimate of their probability, okay? Because you've only got 10 examples of them, and you'd really like to have several thousand of examples of them and the words that they're co-occurring with to be able to make a better idea of whether they are similar or not. And so what you like to do is model those and spend more time modeling them better. The high frequency ones, you usually are modeling very well, and you can remove some of their accuracy because it's not really going to make much difference. But all these sort of low frequency, but not ridiculously low frequency ones, you've sort of got chunky frequencies that are not really giving you a good enough way to measure PPMI, and therefore it'd be better if you sort of gave them more space, more probability space to be able to make better estimates. Okay. Any other questions? Okay, thank you. That's it for today.